So today, what we're going to be doing is I'm going to show you how to design those girts. And then once we design the girts, I'm going to, like I said, I'll go back. Last week we did the whole Gerber. We did the whole Gerber girder. And this week I'm going to continue with the perimeter beams. And after that, we'll talk about the perimeter columns and all that. So I'll do it step by step. And this way, hopefully, from last week to this week, you were able to do all your calculations for your Gerber girder. I mean, give you all the information as well as design your columns. And that should put you, well, a little further ahead with your project. So now what I'm going to do is, of course, share my screen with you guys. Here you go. Okay, so the girts. So let me start with, now, if you guys remember the girts are those horizontal members that go from column to column. And they basically, what they do is, like, when the architect comes and he puts his wall out here, okay, well, the wall envelope gets fastened to the girts. So the girts basically support the wall. That's what they do. And what you need to do, and of course, the wall, you can assume that it's going to get carried by the foundation wall here. So therefore, there's no load on the girt. The only thing that the girt has to worry about is the wind load that is pushing on the wall. So that's what we're going to design the girts for. Okay, so now this is a girt, so therefore we need to know what is the tributary area of the girt so that we can find what are the values of the factors that will affect the pressure on the girt. So therefore we're looking at an area of about 2 meters by 6.52 meters. So this is the tributary area that each girt is going to be carrying. And from here, we can go ahead and, so first I worry about my geometry. And once my geometry is done, now this you've seen already. We talked about this when we did the exterior column, but I'll repeat it. In other words, this is the formula that you guys should be writing down right now. Just a formula that you should be writing down in your notes, because you'll need the formula in order to calculate the pressures. So this is the formula right here.
Can you go back, sir?
Sorry? Go back? Sure.
Yeah, I didn't have time to take the...
Okay, but don't forget, I'm recording this, Vincent, so at any time you can always go back and view the video, if the video doesn't crash on us. Hopefully it doesn't. So far it doesn't. Okay, so basically, is there any questions you have here, Vincent?
No, I don't have any questions, but I just want to copy it down. But I mean, you can go
Sure,
on.
I know. It's good to have the geometry in front of you. I agree totally. And I apologize for going a little too quickly. We have until 8 o'clock tonight before we can call it a night. How's that?
Sounds good.
So your wife's not gonna get mad?
Sorry?
Your wife's not gonna get mad?
My wife, well, she's here, and she's gonna get mad? I don't know. We'll see. If she starts screaming around 7 o'clock, we'll call it a day at 7. Sounds good? No, she knows that right now I'm trying to give you guys the most I can. So if it takes whatever it takes, just to make sure we're well up to speed. So don't worry about it. She's very understanding.
Thanks a lot for that, sir.
Thanks, sir.
For what?
Yeah.
Oh, listen, guys. Look, if I was in your shoes, this is what I'd expect from whoever's teaching me. So I'm doing to you what I would have liked to have done to me. So listen, guys. Hope you appreciate it, and that's all I care. Okay, so here we go. And guys, please, yes.
Are you going to record everything after 4 o'clock?
Well, yeah, like what we're gonna do. This is Giancarlo, right? Yeah. So
Yeah.
Because it's hard for me. Yeah. Okay. Yeah. What I'm gonna do is at about 20 to 4, I'll pause the video. You understand? And then after that, you guys can have a 20-minute break, and then I'll come back at 4, and we'll just continue. Maybe we'll have it all done by. I don't know if we'll have it all done by 20 to 4, and if we did, all the better. And then I can just come back, and if there's any questions, I can keep answering the questions. But I will video the whole thing like I did last week. I paused it, then I continued, and the whole I called lab tutorial was all on video. Yes, I will be doing it. Okay.
Thanks.
Okay. So now, okay, let me just get back here. Okay, so basically, this was the equation to calculate the wind pressures. And of course, you know, we've seen this before, but I don't mind, like, it's good to review. So P is the pressure, okay? And of course, if it's, you know, acting always normal to the surface, that's what we assume. In other words, at 90 degrees to the surface. And of course, if it's a pressure, it's acting towards the surface. If it's a suction, it's acting away from the surface. The importance factor, of course, is what we need to consider when we're designing a building. And in our case, our importance factor is going to be 1. Q is the reference velocity based on the probability of being exceeded in 150 years. Okay. And CE is the exposure factor, CG is the gust factor, and CP is the external pressure coefficient. What this does is that, guys, what they did this year, just to let you know, when they were doing the wind tunnel tests, the results, this kind of adjusts for the results they got on the wind tunnel test. That's what this thing does. It adjusts the external pressure coefficients on the surfaces that they were actually doing the wind tunnel test. So now, the net specified pressure due to wind on part or all of a surface ability shall be the algebraic difference of the external pressure or suction as provided above in the internal pressure and suction due to the wind calculating using the following formula. Now, for the internal, it's very similar. We use P internal. It's the same formula, except you take these three variables, they're exactly the same for these. Now, the only difference is that you have an interior gust factor and you have an interior pressure factor. So that's the only difference. Now, the specified internal pressure acting internally, okay, so that's, and then of course, the IW is the same as used for the external. The Q is the same one that's used for the external. The CE is the same one that's used for the external. The CGI and the CPI, okay, I want to get these values for you in the, I don't know if you guys can see this, but this is the book that I get all the information from, okay? This is a supplement to the National Building Code. This is 2010. They don't change very much over the years. I never bothered that into 2015. Just this thing, I think, sets you back about a couple $100. Thank God the school pays for it. So that's where I get all the values. And now, the importance factor, okay, so you know that there's basically 4 categories for buildings: low, normal, high, and post-disaster. We're in a normal range. So therefore, this is the limit stage design here. So just so that we're all on the same page. Okay, so this here is for limit stage design. Okay, this is LSD. And of course, this is servability limit stage. And that's why when we're calculating the deflections and all that, we always take 0.75, okay? Now, I don't want to bore you, but the reason why it's so low is because the wind pressures are still based on a probability of 1 in 30, okay? And since they brought all the climatic information up to 1 in 50, they kind of lowered the values for 1 in 50 back to 1 in 30. That's why it's there. Clear all the drawings. Okay, so we have the value now of IW, both for strength and for serviceability. Now, this is where we go get the value of Q, and of course, okay, we've seen this before, and therefore we go to Montreal, and we go to 1 in 50, and we have a Q equal to 0.4 kPa. I hope you guys are writing all these values down, because this is what you expect to see in your design brief, okay? So Q is equal to 0.4 kPa. And now for open terrain, of course, the value of, this is the formula to calculate CE. So if CE happens to be less than or equal to 6 meters in height, therefore the value is 0.9. If it goes over 6 meters, then of course it will vary with the height. So it goes from 0.9 up to 6 meters, and then it keeps on increasing, and so on. And of course, H is the distance from the ground to where you're calculating the CE value. And of course, this is a picture of the open terrain. In other words, you know, there's very little trees in the way, and especially if you're along the lake, you're definitely into open terrain. And of course, there's also rough terrain. And I rarely use this. I always use the open terrain. So if all of a sudden I start building on my building, all the better. I'll just feel a little bit safer that I'm a little bit more conservative in my values. Same H values, and of course, So here's your open terrain. Somewhere down here is your rough terrain, and anything along here will still be considered open terrain. So now, this is where I get the value of CG or CECG combined. Okay, so that's why I need to know the tributary area of the element that I'm designing. Therefore, we know that we had a tributary area of about 12 square meters, which was 6.25 times 2. So therefore, I'm somewhere along here. Now, I want to know what the on the windward side. In other words, this is where it's positive. If the wind's going this way, I want to know what the value is here. So therefore, and I want to know what the value is here. So what I did is, of course, I went and I drew a line for you guys. So therefore, these are the values on the windward side, this is on the leeward side, and these are the values of CECG combined for the external pressures, and we're going to be using that in our calculations.
Sir?
Yes.
Okay, John Michael is first.
Sir?
No, go ahead. I'll ask later.
Okay, I just wanted to know the units. Are there any units for this, or it's just unitless?
Oh no, the factors are unitless. Okay.
Okay.
Like G, like these are all unitless. The only one that has a unit is the Q factor, which is the
Okay.
K. Okay.
Okay.
Everything else, they're just coefficients. Instead, they're just unitless.
Okay, thanks.
I'm kind of confused exactly on what exactly is all of this. Like, I don't understand where the values and.
What are these values? You have to understand the equation in order to understand the values. Do you understand the equation? Let's go back. Okay. Let's go back. Here, this is the equation, John Michael. There's the equation. In other words, if I want to calculate the pressure on the surface, I need to know the importance factor of the building. I need to know what the reference velocity is. I need to know the exposure factor. I need to know the gust factor. And I need to know the external pressure factor. So that's the equation. So therefore, I have to go and find the value of IW. I have to go find the value of Q. I have to find the value of CE. I have to go find the value of CG. And I have to go find the value of CP. Now, that chart gives me these two combined into one number. This one, we get it from the formula. This one, we get it from the climatic information. And this one, we get it from the importance factor of the buildings. Is that a little clearer?
All right. Yeah.
So what do you mean you don't understand what these are?
I don't really understand, like, where are you pulling CG and CG and CG from?
It's a graph that you find in this book here. You see this book here?
Right.
That's a graph in there. Okay, last year, let me just show you. So you guys get a, okay? So let me get the ones on wind. In this book here, last year you probably saw, 1 second. I don't know, in structural analysis, you probably saw this graph here. I don't know if I can show it to you correctly, but you see it?
Yeah.
Okay, that's what you saw in structural analysis, but that's only for the structure. In other words, when you design the structure for, okay, that's for the structure. Now, if you happen to be designing something that's going to do with a cladding, this is the figure you got to go to get the values for cladding, okay? And then they have more. If you're doing a roof, that's the one for roof. So there's one for a roof, and then so on. And then if you happen to have a high and low building, so there's so many different figures in here that you could go and get your values of CG and CP. So that's what this book does. And look at this, look at that one, look at for a hip roof, what you have to do to go get the values. So in other words, as you start getting more and more involved into things that are not just square, and you're looking at roofs and so on, then you have to buy yourself this book, and this is the book where you can get that information regarding all the variables that you have in calculating the wind pressures. Okay, so that's where I get it from. So all I did is I copied it, and I'm providing it for you so that you guys don't have to buy the book. Okay, so let's go back to where we were. Okay, so here we did this, and we're going to go back to here, okay? Okay, so here we get the value. So in other words, we have On the windward side, in other words, on the pressure side, assuming that the wind is going to be blowing this way, okay, if the wind is blowing this way, then these values here is for all the surface here. And on the leeward side, the red one, that's for on this side here, on the back side. That's those values. Or even on this side, okay? So, so now we go ahead and we start calculating the pressures based on all the values we found. IW is 1.0, Q was 0.40 kPa. The CE value, since we have a height of 6 meters, is 0.9. And this is what we got from the graph. CPCG was 1.5. Now and therefore we ended up with a pressure of 0. Now guys, I'd like you to just double check this value here to make sure I didn't make a mistake, because I did this relatively quickly. So just check, tell me if this is okay.
Yep, it's good.
It's okay, sir.
Pardon?
It's okay, sir.
Great. Like guys, every value that I put up here, I want somebody to tell me, yes, I've checked it, because this way we'll all have the same value. So therefore, this is the pressure, okay, created on that girt on the windward side. And then, of course, we got to go to the leeward side. And we do the same thing. And now, okay, so I'll leave this on, give you a chance to copy it. All you basically copy this down. In other words, how you calculate your pressure on the windward side, and then how you calculate the pressure on the leeward side. Of course, because I have a negative value here, that means it's going away from the surface. But here, I rounded this to 2 decimal places. So somebody also please check this value for me, and if it's good, we're going to go on.
Sorry, sir.
Yes.
I have a question. So basically, these girts that we're designing, are they only for the long side of the building, or we're going to do another set for the short side of the building?
They're both for the long side and the short side, because the wind can be blowing perpendicular to the long side, the wind can be blowing perpendicular to the short side. So
okay.
As far as which side it is, it makes no difference. And as a matter of fact, the wind can be blowing from the other side there all of a sudden the other, you understand? So this is what we don't worry about which side we're designing for. We're going to try to find, let's call it the highest pressure. And once we find the highest pressure, we'll design them all for that pressure. This way, no matter which direction the wind is blowing, we know we've got it all covered.
Okay. So that geometry that we had at the beginning was basically the same thing for both.
Yeah, exactly. If you look at the short side, you look at the long side, they all have the same tributary areas. Okay.
Okay.
So therefore, like whatever we do for one side, it will be very applicable to the other side.
Makes sense.
Now, if you happen to have different tributary areas, right, remember that in this case here, the smaller the tributary area, the higher the CPCG value becomes in that graph. So that's what you have to be careful about, understand?
Okay.
So that's what you have to be careful about. So if you have 2 different tributary areas and you end up getting 2 different CP values, I suggest you evaluate both and you take the higher value.
Okay.
Follow?
Makes sense. Yeah.
And then I would just design it for one girt and make the same girt all over.
Okay. Perfect.
Okay? Sounds good?
Yeah. Thank you.
You're welcome. Now, I'm sorry, did everybody finish copying this?
Yep.
And is this value okay, 0.58 here?
Yes.
Thank you. So far, so good. Now, we'll just keep going. And now we've got the 2 external ones. Now, of course, we want to calculate the internal ones, okay? And so we use the same formula for that we've seen before. The only difference is that this stays the same, that stays the same, that's the same. This is different, and that is different. Now, I can bore you and tell you that there are basically a couple of values that you can use here, okay? But I looked at the one that was most reasonable for our project, and I chose one for you guys. So here is the internal gust factor. I use a value of 2.0. The reason why I took that is because if your warehouse is going to have these big overhead doors, and if those overhead doors ever happen to be open when a storm comes in because you're unloading a truck, then your gust factor goes up to 2. And that's why I use this. And of course, this here means that your building has reasonable size openings, and therefore I took this value here from the book I was telling you about, the Supplemental National Building Code. Now, if I apply all those values, I end up getting on the windward side minus 0.50. And of course, the nice thing about this one is on the leeward side, they have exactly the same values. So on the leeward side, I still have the same value of the pressure, except this one is positive, it's going towards the wall, and this one is negative, it's going away from the wall. So I'll give you a chance to copy that, and then we'll go on. Well, I just double checked myself. 0.5 is good enough. Emily, is that your dog?
No, I
Oh,
would.
oh looks good.
Yeah, he's pretty cute.
Yeah, I know. Kaylee's got a seal as a pet. It's amazing. She must have a big pond.
I'm gonna change that soon though. I still have the image of your joke this morning.
You still don't get what I said this morning?
Yeah, I said I have to change that soon. When I look at it, I just have the image of seals going to a club.
Yeah, like two seals walking to a club, you understand? And it's a really sad joke because unfortunately the harp seals in Newfoundland, they get clubbed because they seem to eat away all the fishes. So the fishermen go.
No, I know it's pretty bad.
It's a sad joke. It's a sad joke. Okay, so guys, is this okay? Can I go on or just say no and I'll wait? If I don't hear any answers, then I'll just go
30
on.
seconds.
Wait.
Wait, sounds good. In the meantime, Kaylee and I are going to crack a joke. So tell me a joke, Kaylee.
I don't got too many.
You don't have too many jokes. That's okay. Well, we'll just have to sit here. So I'm gonna.
Okay, I'm done.
Good.
Yep.
Sounds good? Okay. Now, this is what happens, right? Assuming that this is the wind direction here. Okay, this is the wind direction here. It doesn't matter. It's just so that you know which way when to push, showing it going toward the surface. So therefore, what they mean by the algebraic difference is that since this one is, I showed it as positive, but since it's going against the wall, it's negative. So it would be 0.54 minus, but you see that they're both going in the same direction. Therefore, you would have to add these two up, and you would have to add these two up. And of course, the higher one is the one that's going to govern your design, and this is the one that's going to govern my design. So in other words, I will be designing for a pressure equal to 1.08 kPa. That's going to be the wind pressure that I'm going to use to design my girts. And of course, it's the same wind pressure I'm going to be using to design my columns because it's the same tributary area. It's just a coincidence. So this is what we mean by the algebraic difference, because this value was negative, this value was positive, they add up together. This one was positive, this one was negative, they add up together, both going towards this way and this one going toward the wall. Now, the external pressure, like I said, is the external pressure minus the internal pressure. And of course, minus 58 minus 50 gives me minus 1.08 kilopascal. That's on this side. And that's, I'm taking the higher of the two, and that's the one I'm going to use to design my wall right here. Okay, that's it. Now, what I need to do,
Can
yes.
can you give me more time to like copy it?
Sure. Just what you have to copy is basically this here. This is just to make you understand why these two get added up together. I have a negative value here and I have a positive value here. It's the algebraic difference of that minus that gives me that. And that's what's acting on the leeward side. And since this is higher than the windward side, this is the one I'm going to be using to design my girts. Okay. Now what I need to do is take that pressure and convert it into a uniformly distributed load along the girt. Therefore, I multiply that by the tributary width that the girt is going to be carrying. And of course, the tributary width is 2 meters. 2 meters here, 2 meters here, and so on. So that's my tributary width. Now, of course, I will be looking at this load case over here, okay, which is 1.4 W. That's the one where the wind becomes a principal load. And therefore, for strength, the wind load is case number 4 at 1.4 W. And therefore, I take 1.4 times 1.08 kPa. And my factored load becomes 2.16 kilonewtons per. Okay. So my WF is my factored load times my tributary width, 1.08 kilonewtons per meter squared times 2 meters. And this will now give me my uniformly distributed load that is acting on my girt. So all along the girt here, okay, I will have 2.16 kilonewtons per meter force acting on that girt. And of course, that's what happens here. Okay, so this is what's it's acting all along the girt from one column to the other column. So, if you guys had a chance to copy this down, so now that I know what load I'm going to be designing for, then this becomes very simple. For serviceability, of course, I want to calculate deflection. For serviceability, now I take the importance factor of 0.75, okay? And therefore, the 1.8 gets multiplied by 0.75. This is the importance factor. That becomes my wind load. I take my importance factor. That's the only variable that changes. And multiply by my tributary width. And therefore, for serviceability, this is the uniformly distributed load that I will be using to calculate deflection. This is for strength. This is limit states design. And this is for serviceability. Serviceability limit states.
Sir, I have a question.
Yeah, go ahead.
You know, for the factored load,
Yes.
it's 1.4 times 1.08, and when you found your you didn't change, like, it's still 1.08 times 2 meters. It's not like the factored load.
I forgot to multiply it by 1.4.
Yeah, I think yeah.
Well, it's possible. Like I told you, I did this quickly.
I think.
So everything's going to change from here on in, because the rest of the slides times, yeah, it becomes a 3.02. I agree totally. So I forgot to multiply. Yeah, because I forgot to multiply this right away and get my value. Okay, so that's what I'm going to do. Hold on a second. I'll just. Okay, so this is supposed to be equal to 1.4. Good. This way we'll all be designed at the same time. Times 1.08, and therefore this becomes 1.512, and therefore I'll change this to 1.512 multiplied by 2, and this becomes 3.08. I'm sorry, 3.02. And of course, this is going to change also. Oh no, this stays the same. Sorry, this stays the same. In other words, just important factor. So that changed our load to 3.02. That's going to change everything that we're going to be doing from here on in. Okay? Thank you, Vincent, for pointing that out.
No problem.
Okay, so now this becomes our WF. So what I'm going to have to do is I'm going to have to change all the values from here on in, all the way through. So it'll be fun. We'll all design this whole thing at the same time. Okay, so, wow, I forgot to.
So for the serviceability, you don't factor it. It just stays at.
No, like the
1.08.
serviceability, like in other words, this is your load factor for the wind, right?
Mm-hmm.
For serviceability, you take your service load, and then remember the importance factor was 0.75.
Yeah.
Okay, that's why we reduced our wind load by 0.75 for serviceability right here. So it doesn't get multiplied by no load factor. But it only, like in other words, I go back to the equation, Vincent, the only variable that changes when I calculate my W is my IW, my importance factor. And for serviceability, it becomes 0.75. So this stays the same. So now we have a WF, so therefore our factor load is 1.512 kPa. Okay, that's good to know. Okay, so that's going to change everything we're going to be doing today. It's good. Okay, so let me go back. Let me go to the next slide now. Okay, now I'm going to have to change this. This becomes, what do we say this was? 3.02?
Yep.
Yeah, 3.02. That becomes 3.02. That's good. Now, of course, this changes. Well, I'm glad. 3.02. Oops. And of course, that stays the same. So now, guys, I want you guys to do the calculations with me to make sure we all get the same values. So now here I get 14.8. And here I get 3.02. Two times 6.5 divided by 2 equals 9.4. Oops, 9.4. So is everybody in agreement so far with these two values?
Not there yet.
Sounds good? So this is good and this is good? We agree?
I didn't calculate it yet.
The first one is good.
Okay, great. First one's good.
The second was good too.
Okay, so they're both good. That means those are the two values we're going to be designing for. So we have MF is equal to 14.8 and VF is equal to 9.4. Now, would somebody just double check this number here? Since we haven't changed the, this should be the same, okay? I just want somebody to double check to make sure that that's okay.
Yeah, it's good.
Great, so that means,
Sir,
yes,
where'd you get 1.62?
1.62. Oh, that's where we got this from the previous, we got that from here for serviceability, 1.62.
Perfect, thank you.
Okay, that's where we got that from. In other words, and I know that one was correct because the only thing I changed was a 0.75. Okay, so here we go. So here we've got, this is the IX required, 9.3 times 10 to the 6, the VF of 9.4, and the MF of 14.8. Now, guys, I hope you can appreciate, okay, this is my girt here, right? Here's my girt, and basically all it is that it's being supported from column to column, right? And there's the load that's being added to it, and therefore it becomes just a simply supported beam, you know, and we design it the same way you would design a beam. The only difference is that this beam is now going, you know, it's acting, the loads are acting horizontally against the beam. And what we tend to use for these girts, okay, like you have two choices. You can either use what the most typical shape that we use for girts. It's either, they call these cold form channels. They look like this, okay, or just in the old days before we had cold form channels, we can use regular channels. So what we're going to do is that since you guys don't have the tables for cold form channels, we're going to just look for regular channels, and that's what we're going to be doing. And of course, these channels, okay, you put the strong axes here. This is the strong axis, and you put that in the direction of the wind. So in other words, these things will be placed like this, okay? These things will be placed like this because the wind is acting this way, and this is, and so therefore that's how you place the channels. Okay, so now we're gonna, this is good. Now we're gonna go, okay? So here, I have an LU, of course, this is no good anymore. This was 14.8. And this was 9.4. Now, this is no good anymore because I made a mistake. So now what I'm going to do is, of course, okay, so here, it's just like you did when you went to choose the, okay, this is the beam selection table. Now, this is what I was going to choose, but I made a mistake. So now I got to look for an MF that's a, here. I know that I have an LU of 6.25, so I am somewhere around here, okay? Now, I'm not going to go up to 7. What I'm going to do is I'm going to try to find an MR that's slightly higher, and this looks like a good value right here, okay? This looks pretty good because we have an MR of 16 and we need 14. So even if it's slightly longer, I know my MR is still going to be over 14.8. Or, see, now you've got to make a choice here, guys. We can easily use a C230 by 22. Okay, in other words, and that is going to give me an MR of about 15 point something because I'm somewhere around here. Or I can use a slightly higher, a higher weight, okay? C200 by, let me clear this. I can use a C200 by 28, this is higher. Now, the choice you make, let me just see, I can't get rid of this one. Okay, so this is no good anymore. Now, what happens here is that you got to make a decision, okay? Like if it all depends on, okay, it all depends on the architect. It all depends on, you know, there's a number of factors. Let's say you make your exterior column. This is a plan view of your exterior columns, okay? These are your exterior columns. Now, your exterior columns, you know, this is a plan view of your exterior column here. Both your wind columns and everything else, okay? And so on. Now, if you design your exterior columns W200 by something, okay, then you know that the nominal depth of your column is about 200. Now, if you want your channels to stay within the distance of your column, then you should be using a C200. A C200. In other words, this channel here, this one here, will fit in between your W's of 200. So therefore this, now, if that's not critical, if you put your, of course you'd have to go flush on the outside, and then on the inside you would go slightly more if you use a C230. Now, if that's not critical, then this is a better choice because it's lighter, right? And of course, you talk to the architect, and if the architect likes to create this gap between the columns so that people can pass wires or pipes or whatever, then this would be another choice. So it all depends. This is something you would coordinate with the architect. Does he mind losing this extra 30 millimeters inside his building? Or does he want to keep the thickness of the wall down to 8 inches? It's up to, you know, this is things that you discuss with him. So if you're looking at it strictly from, a weight point of view, in other words, you don't care, then you would go with the 230 by 22. And if all of a sudden the geometry becomes important for the architect that he doesn't want to lose this extra 30 millimeters because his layout here is so tight that he can't afford to even lose this extra 30 millimeters, then that's going to be another choice to make. So for now, we'll assume that the architect is a mind, so we are going to go with we'll go with the lighter one. We're going to say that all our girts are going to be this one right here. Okay. And of course, we get up an MR of 16. We have a VR here of 294. So we have an MR of 16 for an LU of 6,000. We have a VR of 294, and I have an IX of 21.3. Okay, so those are the values. So therefore, can somebody, what do we say? Sorry, we said it was going to be a W200 by 230 by. Can somebody just tell me what we picked?
230 by 22.
By 22. Okay, that's the one we're going to pick. And of course, here we're telling everybody the LU that we picked is smaller than the LU provided. Okay, the LU. Okay, so therefore we got to be careful. Therefore here, I'm going to put my MR value of 16. Now, I'm not worried because if I actually do a calculation, I know that when I go up to 6.25, I'll still be higher than 14.8. So therefore, I'm giving myself sufficient. And of course, here I'm going to change this to 294. And of course, this changes. That's 235, which is way ample for the shear. And of course, our IX value was 21.3. Wow, that's really good. And that's going to be it for the girts. So therefore, we'll make all the girts. We're going to specify in our drawing that all the girts are going to be C230 by 22. Okay. Now don't forget. Slideshow. Okay. Now don't forget that this is for this. Okay. See, so you can specify that the channels can be G40.21 300W steel. They don't have to be the 350 because this table is based on. So therefore, on your drawing, you should specify that all shapes to be whatever 992 ASTM for all W shapes, and for all C shapes it could be G40.21 300W. Okay, so that's it's a weaker steel. And believe it or not, that's it for the girt design, guys. So.
The The VF, you have to change it too. The VF that you kept it at 6.75, but it's actually 9.4 now.
Oh yes, I'm going to change that. Thanks, Mason. Appreciate it. Oh yeah, there's one more thing we need to do. Okay. So now, hold on a second. So here you said this was 9.4.
9.4.
9. Okay. See, mistake slipped in my calculation, and it had a big effect on the final choice. Okay. And that's why I say, guys, always have your calculations double checked by somebody else so that you can accidentally oversee something. Of course, if I was doing this, I know I've got 30 good students that are checking me as I'm going along, so I feel a little bit more comfortable. But if I was doing this on my own, I would do it once, put it aside, the day after, type it up Jose, I'd come back and recheck everything to make sure I haven't made a mistake. And of course, maybe I would pick up the fact that I forgot to actually multiply those two numbers, and therefore it had an impact on my total design. Now, as I said before, okay, excuse me. Now I need to go and find something in my steel book. So we're using a C230 by 22. Let me just go get something in my steel book here. C230. Okay, C230 by 32. Oh, by 22, sorry. C230 by 22. Okay, great. Now, I'm just going to keep going. So keep in mind, okay, that the channel is being, like if I draw a cross section here, okay, you're going to be putting the channel like this. It's going to be placed like this. In other words, this is a strong axis, so therefore it can resist the wind, okay? That's the strong axis, and this is the weak axis, okay? Now, what happens with these channels, because they are fairly weak above the weak axis, okay? These things tend to sag when you actually place them, okay? They tend to sag. In other words, they will deflect under their own weight. So now, what we want to do, okay? So now what I want to do is, I'm going to go, okay. So here, I should escape. I shouldn't have done it this way. So I'll do this way. This is C230 by 22. Now, this channel is going to weigh 1.29. Okay, I get this straight from my steel book. This is how much this channel weighs, 1.29 kilonewtons per meter. And the IY for this, channel is 0.805. Okay, so that's the IY. In other words, that's the weak moment of inertia. So here I'm going to put the value of 2.19. Here I'm going to change this to 0.805. Can somebody do this calculation? I'm going to do it also, but somebody do this calculation. 805. And of course, I'm going to do it. I want other people to do it. 5 times 2.9.
Sir,
Yes.
where did you get the 2.219?
0.219. That's the weight of the channel. Okay.
Okay.
Like Ramelin, is that you?
Yeah.
Okay. See, Ramelin, this here means it's 22 kilograms per meter.
Okay.
That's the weight. Now you got to convert it to a force. So if I take my 22 multiplied by gravity, 9.801,
Okay.
divided by 1,000, and it should give you this answer. Is that what you get?
Let me check.
In other words, I took it straight out of the steel book, okay? The steel book tells me it weighs 0.219. Now, if I want to check the steel book, I take 22 times 9.81 equals 22 times 9.81 divided by 70. Yeah, 0.21. Yeah, it's about, that's what they're saying it weighs, okay? Now,
Thank you, sir.
Okay, so I mean, this is accurate enough. Now, the reason why they added, make it a little bit higher, because sometimes the tolerances can make it a little bit thicker, so they give you the upper value of what these things can weigh. But this, even if I were taking the 22, it would have been accurate enough, okay? So now, I take, take these values, I take 5 times 0.219 times 6250 fourth equals divided by 384, 200,000 divided by 8.
I get 27 millimeters.
Okay. I'm almost there, Mason. You get 27?
Yep.
Yeah, that's what I get. I get 27 millimeters, okay? 27, of course, divided by, so it's approximately 1 inch, okay? 1.1 inches approximately, okay? Now, what happens is that, let me make you understand here. So here's my column, and here's my column, okay? Now, this is the perimeter beam that we have on top of the column here, okay? I should have drawn it. Hold on, let me just. I'm going to draw it properly so you guys make sure that we. Okay, so here's the wing column here. This one is below the beam. Then we have the perimeter beam that goes on top here. And the other two beams, it's going to be side loaded like this and like this. And the girt is here. And the girt is there. Okay. And there's the girt. And there's the girt. Now, what happens here is, okay, so these girts are going to sag, okay? Under their own weight, they're going to sag about 1 inch, a little bit more than 1 inch, okay? So what you do that to prevent the sagging, and you want to keep them straight, what you do is you put these sag rods attached to the beam up here, okay? And these are basically, they're just 1/2 inch diameter rods, okay? And most likely, these things are threaded all the way through, okay? So what they do is they put a rod here, and then it goes through the channel, and what this sag rod does is they use it to prop it up so this is nice and straight. So that's what these sag rods do. So you have one there, and you have one there, and they're one beside the other. So what these sag rods do is they prevent the channel from sagging, and of course, then all this force gets transferred up here to the perimeter beam, and of course, when we do the perimeter beam, I'm going to be adding this force onto the beam, okay? So, sorry?
Sorry, go ahead.
For girts, you wouldn't camber them, right? Or what is it
No, because you
wouldn't
don't.
do
It's
that.
not a question of cambering. You understand? It's a like you don't. You wouldn't camber them like to compensate for the sagging. It's much cheaper just to put these sag rods in.
Yeah, that's kid.
Understand? It's much
Just
cheaper
to
to
make
put these
sure.
sag rods in than it is to actually camber them. So that's why we have these sag rods. Understand?
Sir,
Yes.
I don't visualize it. You attach it to the.
Well, now I'm gonna draw it in this section. Okay, so this is an elevation, right? This is elevation. Okay. Now I'm gonna draw a section. Okay. So what happens here is that this is the perimeter beam sitting on top, like this, and here's my channel here, like this, and here's the other channel here, like this, right? So far, so good, right?
Mm-hmm.
So what happens is they put the rod, they put it here like this, okay, like this. And of course, they have a nut here, and they have a nut here. And then right beside it, they put the other rod, and they go support the one below it. You see how it works?
So that would just be like sitting in the wall, right?
Oh yeah, that would be right in the wall, exactly.
You don't see it at all. It's
You
just
don't know, exactly. Once the wall, because the way that these industrial buildings are built is that out here, they use these prefabricated panels that go straight across here, and they've got all the insulation, everything they need, right? And then this is all exposed on the inside. Understand? So, and then if the architect wants to finish it, then you can finish it with some kind of wall finishing. But this is all inside the wall, exactly. Okay?
Okay, so sir, the sag rods, we just like include them in our calculations.
No, the sag rods, you just show them on your drawing. Instead of just say sag rods. Instead of
No, but
diameter.
for the other calculations, you said you were gonna include them.
Well, I mean, like what we're doing here is like we're trying to determine, like, do you want to live with a 1-inch sag in your girts, or do you want them to be nice and straight so when they come and attach the wall panels to it, they'll stay nice and straight. Everybody likes to keep everything nice and straight, right?
Yeah.
And that's what these things do. They allow the things to stay straight so that when they come and attach the wall panels, once the wall panels get attached to the girts, these things become pretty redundant.
But don't these add like a dead load to the beams on top?
Exactly. Now we're going to throw that into our perimeter beam. Okay.
Yep.
But let me just clear the drawing. That's exactly what it does. Okay. And we're going to throw this into the perimeter beam, but it doesn't have much of a load. Okay. So here, this, okay, 1.25. This was this is, I'm sorry. This, I have to change this value here. I have to change this value. This was 29. Okay, so I have to change this value. So I got 1.25 times 3.125 times 0.129 times 2 girts, and that gives me 1.71. Okay, so that's the dead load that it adds to the perimeter beam on top. Okay. And of course, that is equal to.
But that wouldn't make a big difference because.
Oh no, it doesn't it makes hardly any difference. In a sense, it's like it's only about, like, it doesn't make much of a difference.
Because our perimeter beams are usually all like over designed on.
Well, they are, and
shear.
like you said,
So, like,
and then don't forget, like once the wall panels actually get attached to the girts, okay, the wall panels now start supporting the girts, right? So like even that, it can become pretty redundant once the wall panels are in. Okay.
Yep.
So
So do we change the weight, or you think?
yeah, I'm going to change it. So in other words, this comes out to about 385 pounds about. Okay. 385 pounds, just about. Okay. So let me just take this weight down. So I have 1.71
Wait, how much?
kilonewton that the sag rods are going to add to the perimeter beams.
Sir,
So I'm glad I screwed up. Yes.
how exactly do you know which rods you need to use for sag rods?
Oh, look. Well, it's very simple. You let me just erase. Let me clear the drawing first of all. Okay. Well, John Michael, these rods, like 1/2 inch is a standard rod diameter. 5/8 of an inch is a standard rod diameter. Okay. And you know, if you actually, these things are acting completely in tension. Okay. So a 1/2 inch is usually more than ample to provide the resistance to hold the thing up. So, I mean, if you want to get fancy about it and you want to start looking, can I get away with 3/8 of an inch? But a 1/2 inch diameter threaded sag rod is probably the most common thing that they use. Understand? Like these things come like in lengths of about, I don't know, 20 feet, and then what the guy does, he just cuts them to the length he needs to make the sag rods. Understand? So I can tell you that if I would calculate the, in other words, if I would take the formula TR is equal to phi Fy, you know, AGFY, and I take the diameter of a 1/2 inch rod, I'm sure that I'm going to exceed, even if I take the cheapest steel, I'm going to exceed 1.17 kilonewtons. So that's if I want to make sure that, now, okay. And
Sure.
yes,
I think you made a mistake. It's 385 pounds.
385 pounds, right? Yeah, no, that's what it is. It's 385. That's what it says on my calculator. I have 384 points. Yeah, it's 385 pounds. I wrote it the other way around. Thank you.
No problem.
Okay. So guys, that's it. So now we know that all we're going to do is specify C230s by 22s for our girts. And we're going to specify 1/2 inch diameter sag rods. And that will cover the girts. And we know that the girths add, or the sag rods add a total of 1.71 kilonewtons to our perimeter beam. Okay. Now guys, how did I do this calculation? It's very simple, like this one down here, so that you guys are on the same page. Okay. Okay, so basically this is the girt, right? Here's a sag rod. Okay. So, and this is how much the girt, sorry, shouldn't do this. Okay. So just like, for example, the formula I gave you, just like the formula I gave you when you have a continuous beam, okay, like this, okay, the reaction here was that coefficient of 1.25 times the W here, okay, and therefore, and of course, this is the span here of 3.25 meters, half 6.25, and that's how it ends up getting. So 1.25 is that coefficient that I showed you once in the lab. This is the length of one span. This is the uniformly distributed load on the span. Of course, we have two girts. Therefore, I'm adding 1, 2 that are going to go up to the beam. And that's how I end up getting that value there. Okay. So that's pretty well finishes the. That pretty well finishes the girt design, and I'm glad I screwed up. This way, it gave me a chance of showing you how how quickly you can go back and correct yourself from the beam selection table. And I'm going to move on to the perimeter beams if nobody's got any questions. Is everybody okay?
Yeah, just give me a minute. I need to get more paper to write on.
Okay, but like I said, if you're missing anything, I am recording this, and I will be sending you the video once it's done. Okay. Let me save this. Okay, so let me just end this one. Now, I'm gonna have to make a little correction on my, okay. So this was, okay, so guys, this was this is the perimeter beam on the long side, okay? And just so that we're all on the same page.
We can't hear you, sir.
Oh, I'm sorry, I didn't share this. Is that it?
So you're starting to lag
Yeah,
out.
your Wi-Fi's
Okay. Can you see it now? Oh, my
Yeah.
internet connection is unstable. Is this okay now?
Yeah.
Can everybody see what I'm doing?
Yeah, we can't hear you.
Yeah, you're lagging.
You can't hear me? Is that it? Hold on a second. Can you hear me now? Hello? Somebody? Will somebody please talk to me? I want to know if you.
Because last week there was a lot of things I realized that I already had, so I thought maybe like you
Yeah,
reached.
Joe, you're not crazy.
Okay.
Yeah.
Like even today when he did all those internal pressures and external, I have all that written already.
Yeah, it's a lot of double.
I just rewrote it, the whole thing.
Okay,
Yeah, we already have all that in our
and
notes.
we did that when we did the external columns. Okay? Same thing.
That's why.
Anyways, guys, it's good to review. You know, they say repetition reinforces remembering. So, and I apologize for the.
Is it okay, sir, that you have it twice in my calculations?
Oh yeah, by all means. I mean, like it's
You're
nice.
saying you didn't realize you did the same thing twice?
Yeah.
Well, see, like the ones that realized the calculating, and the ones that didn't, well, copy it twice, you'll remember it more next time. How's that? Okay, sorry, I got disconnected, guys. You know, like that's what happens with the internet. And why
Do you
not?
think you lost the recording?
I don't think so. I don't think so. I think it's still recording. And because I haven't paused it or anything. Let me pause it. It started. It's back on, so it's recording.
Okay. Because when you left, I think it stopped recording. I didn't see it at the top of the
It
screen.
probably stopped, and now, because if I press